Hello, good evening everyone. Welcome to the week 5 live interaction session for the course Waste to Energy Conversion. I hope I'm audible and my voice is clear. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session for today. So, let me just share my screen. So, good evening everyone. Welcome to the week 5 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasenjit Mondal sir from the Department of Chemical Engineering IIT Roorkee under the NPTEL SWAYAM program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering IIT Guwahati, Assam. I am one of the course team members responsible for conducting the live interaction session for this course Waste to Energy Conversion in Jan to May 2026 semester. So almost 50% of our course is completed so far, and we have completed our learning on the thermal conversion route. So in the waste to energy conversion process, if you able to recollect, there are totally three different types of processes. The first one is the thermal conversion route, second one is the biological conversion route, and third one is the chemical conversion route. So in thermal conversion route, we discussed about three different types of reactions. One is your combustion, or also so called as an incineration. Then next one is was your gasification, and then the third one was the pyrolysis. So in the last lecture, we ended our discussion on the thermal conversion route. So the pyrolysis process was the last process, and we ended our discussion on pyrolysis process, and after which we discussed about something so called as densification of solids. So I hope everybody is able to recollect about the three different types of processes, such as of the incineration, gasification and pyrolysis process, and what is its primary difference. So it is nothing but it is the oxygen to the fuel, or you can say the biomass feed ratio. So if the oxygen is going to be in excess, the process is called combustion. Anywhere if the process is carried out in a controlled manner or in a controlled oxygen atmosphere, that process is called gasification, where the R value is somewhere between 0.68 to 2.5. when i mean when I say the when I say R value, I basically mean the ratio of the fuel to that of, ratio of the oxygen to that of the fuel. Then the third process is pyrolysis, which is typically carried out in a limited supply of oxygen. So where the R value becomes less than 0.68. So in relation to that, we also discussed about that if we use different concentrations of oxygen, then what type of combustion products expectable are expected from the process. So in case of incineration or combustion process, predominantly it's going to be CO2 in H2O, as the concentration of oxygen is very high. Similarly, if we as we go on decreasing the concentration of oxygen, we are more likely to get carbon monoxide and hydrogen gas. And in case of pyrolysis process, if you see, since the process is entirely conducted in a limited supply of oxygen, you are always going to be left out with carbon monoxide and hydrogen gas along with the solid carbon in the form of char. So these things you actually need to remember, because this forms the basis for the classification of the thermal conversion process and how they typically differ. Other than this, we also discussed about for each of this process the different types of reactors that is involved in them, their advantages and disadvantages. And in case of gasification process, we went to deal more with the syngas production. So I hope everyone will be able to remember that the mixture of carbon monoxide and hydrogen gas is a synthesis gas or a syngas. And if you use air instead of oxygen for the gasification process, the gas stream that will be released as a product will contain significant percentage of nitrogen in them. So the syngas can also be called as a producer gas. So these are the fundamentals that we discussed in the last four live interaction session, and in continuation to that we discussed about densification of solids. So primary reason for the densification of solids, anyone is able to recollect what is the fundamental principle of what is the fundamental need behind the solid densification? Why do we do densification of solids, or you can also say why do we produce briquettes or pellets? Anyone quickly? Yeah, so it helps to improve the energy density of the fuel. So by doing densification of the solids, you try to increase the density of the material, and thereby very small volume of the fuel, or you can say the solids, are required for producing the same amount of energy. So that basically helps in the reduction of the cost, the transportation cost that is required in order to produce a certain amount of energy gets reduced. So that becomes the primary need, or basically the fundamental need, why we actually go for the production, why we typically go for the densification of solid process. So today, in today's live interaction session, we will also deal not just with the, so our discussion on production of briquettes or densification of solids ends in the last live interaction session. What we were left out, or we were not able to continue in the last live interaction session, was the concept of energy improvement. So today, in this particular live interaction, our focus will be on to cover the energy improvement and the energy production from plastic waste and the gas cleanup. So we will be totally discussing about these three different concepts. They are typically very short, very small concepts. So I hope we will be able to cover in another 20-25 minutes. So let's start with that. So in case of the, if you see energy efficiency of the thermal power plant, so how do you improve the energy efficiency? So as our course says, waste to energy conversion. So when, as I also discussed in the last live interaction session, that how industries typically want to improve their efficiency of extracting energy, or their energy efficiency at a very low cost. So what they typically want to do is they want to improve the efficiency of the process, but that should happen at a rate in such a way that the input cost to the process is not very high. So one way to do is to basically improve the efficiency of a plant. So that is how they try to enhance the profit margin of a particular process. So here first, since our process all is concerned about the thermal conversion routes, so we will first discuss about the thermal efficiency. After discussing about the thermal efficiency, we will basically go on towards discussing certain parameters on how these overall efficiency of a thermal power plant depends upon the efficiency of the multiple, you can say, components that is involved in the in the energy production process. And then we will basically move on towards the energy production from the plastic waste. So thermal efficiency is typically, as you know, efficiency as such means output by input. So thermal efficiency, if you want to define, it is typically defined as how much amount of electrical energy you are going to get as an output to that of the fuel input. So let me just write that down. So thermal efficiency is equal to electrical energy output by fuel input. So basically it says that how much amount of the fuel do I need to put, or if you can also say it in this way, that if I basically put, or you can say if I basically feed certain amount of a fuel as an input, how much electrical energy will I be able to derive from the particular process as an output. So that's how you actually define an efficiency of a process. And since here we basically deal with deriving or extracting electrical energy from the system, our output is nothing but it is the electrical energy. So this is the typical definition of the thermal efficiency of a particular process. So if you want to express this thermal efficiency is also expressed as energy generation rate times T by mass consumed, or you can say MC times CV. So thermal efficiency, as if you see in the numerator, it is energy generation rate times multiplied by time. So that typically gives us the electrical energy that is going to get generated out of the process. And the fuel input is usually given as MC times CV, where MC is nothing but it is called as mass consumed, and it can also be expressed as quantity of the fuel, or you can say fuel consumed. And the CV is nothing but it is the calorific value of the fuel. So MC times CV will basically give you the fuel energy that you are typically going to give as an input, and energy generation rate times T will basically give us the electrical energy that you are going to derive as a output from the thermal power plant, or you can say yeah, thermal power plant, or you can say a pyrolysis or any kind of thermal conversion equipment. So apart from that, you also have another parameter that we have to discuss. So thermal efficiency of a particular power plant can also be expressed in terms of a heat rate, where heat rate is nothing but it is 1 by thermal efficiency. It is inverse of thermal efficiency is called as the heat rate of a particular system. So if you see the overall efficiency, as I said, the if you talk about the entire process, so it's not just that your gas is going to get enter inside a black box, and or you can say you are going to feed in your fuel and air into a black box, and from there you will basically get the energy. So it's not just going to depend on the efficiency of your, or the thermal efficiency of the entire power plant is not just going to depend upon one particular component, or the efficiency of a one particular component, but it is actually factors, a series of components efficiency is involved in order to calculate, or in order to obtain the overall efficiency of a power plant in converting the waste to energy. So that's how we have to write overall efficiency is nothing but it is a function, or you can say it is the product of the boiler efficiency times turbine efficiency times generator efficiency times work efficiency. Now all these factors, or all these the efficiency of all these particular component will affect your overall efficiency of a particular process. So when we deal with power generation, we are supposed to basically discuss about some of the thermodynamics that is concerned, or that is involved in in the power generation process. So basically to say, we have to basically understand or discuss about the thermodynamics that is involved in the power generation process. So typically most of these thermal power plants usually use, or you can say most of the energy, that thermal energy that gets produced from these power plants are based on the two different types of cycles. The first one is the Rankine cycle, and then the second one is your Brayton cycle. So these two cycles basically help us to understand the process of energy generation. or you can say it helps us to understand the thermodynamics of the power generation process, because the entire power that gets generated to the thermal power plant will depend upon these two cycles, that is a Rankine cycle and a Brayton cycle. So if you see in case of, so these two cycles are fundamental thermodynamic cycles. So a detailed understanding if you are basically looking for, then you can actually go and look for it in any of the standard thermodynamics book. So you'll be able to have mechanical thermodynamics book, so you'll be able to have a deep discussion, you will be able to find a deep discussion on these two. But here in this live interaction session we will discuss each of them in a very simpler form, so that we don't get too much involved into the thermodynamics of the process, but at the same time we do not lose the fundamental understanding of both the process. So the first one is called as a Rankine cycle. So in Rankine cycle, if you see, you basically have four different types of processes. The first one is the adiabatic compression. Second one is the isobaric expansion. Third one is nothing but it is the adiabatic expansion, and fourth one is isobaric compression. So how many of you here actually have an understanding on the terms isobaric and adiabatic? Anyone is here some of you may not be familiar with these terms. So I hope all of you are familiar. So in case if anyone is familiar, can you please tell us what do you actually mean by an adiabatic process and an isobaric process? I mean, these are something which we have already learned in school level, but again, some of us may have forgotten or may not be in touch. So if any of you know the meaning of adiabatic process and isobaric process, you are welcome to let me know here, so that it will be helpful for all of us. Yes, anyone? What is an isobaric process and an adiabatic process in a So isobaric process is a process where the pressure is actually maintained constant, and adiabatic process is a process where, yes, what is an adiabatic process? Anyone? I told for isobaric, it is a process where a constant pressure, or where a constant pressure is maintained or there is no pressure change. What is an adiabatic process? Adiabatic compression is a thermodynamic process where, typically speaking, an adiabatic process is a process where there is no heat exchange. If to say in a mathematical way, dq or delta q is going to be 0. No heat is actually going to be exchanged in that particular process. So that is the typical meaning of adiabatic process and adiabatic process and the isobaric process. So here we have four different processes. First, there is an adiabatic compression. After that, you have an isobaric expansion. Third thing is adiabatic expansion, and fourth process is isobaric compression. And if you want to see these processes graphically, you can actually see this one. So you have 1, 2, 3 and 4. Let me just move. So these are the four processes. Initially you have an adiabatic compression. After that it's isobaric expansion. Then you have an adiabatic expansion, and then you have an isobaric compression. So in what happens in adiabatic compression? What usually what happens is the pump basically compresses the liquid. So you basically, so this is mainly used for steam turbines. So in case of a steam turbine, the water basically enters inside a pump. That pump, without any kind of an heat exchange without any kind of a heat exchange, compresses the liquid. This compressed liquid is then sent to a boiler. In a boiler, isobaric expansion takes place. So what is typically the role of a boiler is, the boiler helps to the boiler usually converts the liquid to vapor under constant pressure. So first you have the pump. Without the pump actually compresses the liquid without any kind of a heat exchange happening into the system. This compressed liquid then enters into the boiler, where the liquid is actually converted to vapor at a constant pressure. This vapor is this happens till the isobaric expansion. Now what happens is, this vapor actually goes to the turbine, where it undergoes expansion. Again, this process, here the energy of the vapor remains conserved. There is not going to be any heat exchange. So that entire whatever the energy that the vapor is carrying with it, that it enters inside the turbine, and then there it undergoes a adiabatic expansion. After which then once it expands inside the turbine, runs the turbine and generates the electricity, that particular vapor then moves into the condenser, where it undergoes isobaric compression again to form the liquid, where the vapor is actually turned into a liquid under constant pressure. So it's typically, first you have liquid, that liquid is first compressed, and then it is basically sent into a boiler, where the liquid is converted to vapor. That vapor basically carries energy, right? So that vapors enters inside the steam that enters inside the turbine, and then the turbine rotates, generates electricity. Once the vapor loses its energy, it moves to the condenser, where the vapor is converted once again to liquid, or you can say the vapor is compressed to liquid. So this is what typically happens in case of a steam turbine. So here the liquid is usually water. So if I want to let's say talk about the entire process once again, in by using water in as the liquid. So what actually happens is, the water enters inside the pump compresses it, and then pushes the water to the boiler. The boiler, at constant pressure, it heats the water, which then basically gets converted to water vapor. The water vapor now moves to the turbine, and it rotates the turbine, generates the electricity. Once the steam loses, or water vapor loses its energy, it then moves to the condenser, where it undergoes compression to form water once again. So this is a process that happens in the steam turbine, and it typically follows the Rankine cycle. So if you want to see define the efficiency of this steam turbine, this is how you define. Eta turbo is equal to the work done by the turbine divided by Qin. Qin is the amount of heat that we are feeding it into the system. So this is for the Rankine cycle. Now you have a Brayton cycle where we define the process in terms of isoentropic and isobaric process. So if you see here, process 1 to 2 is an isoentropic process, whereas process 2 to 3 is an what it would be, isobaric process. Then 3 to 4 again becomes an isoentropic process. After that, the 4 to 1 again, back from 4 to 1, it's an isobaric process. So as now I have explained for a Rankine cycle, what happens in case of a Brayton cycle? So Brayton cycle is typically used for the gas turbine. Rankine cycle for steam turbine and Brayton cycle is for a gas turbine. Based on that, now we need to, same process happens in both. It's just that in case of a steam turbine, you usually use water or steam to run the turbine, whereas in case of a gas, it is typically air is used to run the gas turbines. So now based on this Rankine cycle, can anyone tell me what happens in the Brayton cycle? Yes. So we discussed on Rankine cycle. Now Brayton cycle you need to explain. I mean you can just say it in simple words. Same process is usually followed. Instead of liquid or water, here we use air. So now you just need to tell me what happens in process 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So in case of 1 to 2, it's an isoentropic process. So what usually happens is air is basically pressurized. So the pressurized air now basically now enters a combustion chamber. So that process typically starts from 2 to 3. In 1 to 2, the air is just pressurized to the air is pressurized in process 1 to 2 in, and then this pressurized air enters inside the combustion chamber. So in the combustion chamber, using this pressurized air, the fuel is burnt, which raises the temperature of the air. That is the reason if you see there is a Q in, because it raises the temperature of the air. Heat energy is provided by the burning process. Now with this amount of with the increased energy as well as that of the temperature, the air enters inside the gas turbine. That happens at process 3. This pressurized air along with the this pressurized air at high temperature, when it enters inside the gas turbine, it expands through the turbine and then basically makes the turbine rotate, which generates the electricity. Once that happens, the air then enters inside a condenser, or you cannot say it's as a condenser. Just a second. So it then enters inside the condenser where the heat is rejected, that you can see in process 4 to 1. The heat is rejected in that particular process. So this typically completes one Brayton cycle. So just like Rankine cycle, where first water enters inside the system, or you can say water is pressurized through a pump, it then enters inside boiler where the water is converted to vapor. That vapor is then goes through that vapor is then sent to the turbine. It expands through the turbine and rotates the turbine to generate the electricity. The vapor or the steam is then sent into the condenser where it is converted back to liquid, or you can say water. In case of a Brayton cycle, which is used for a gas turbine, air is first pressurized, and then this pressurized air along with the fuel is burnt inside a combustion chamber, which raises the temperature of the air. That is represented as Q in. So the heat energy is given to the air in the combustion chamber. Once the air is heated up, this heated air enters into the turbine or expands through the turbine, and basically results in the so when it enters into the turbine and expands through the turbine, the work is basically done on the turbine, which basically causes the turbine to rotate and the electrical energy is taken out. That air, once its work is done, it loses all of its energy and then return back to its initial stage. So this completes one Brayton cycle. So this is about Rankine and Brayton cycle. So as I said, the thermodynamics behind this process is, I mean, the entire cycle's explanation is far more, you can find it in more detail in some of the mechanical engineering thermodynamics books. Here we just discussed on how these two concepts of Rankine cycle and Brayton cycle is relevant to the steam turbine and the gas turbine process. We haven't gone inside each of these processes in much detail. We just looked up at how it is used in case of a steam turbine. So any questions so far related to Rankine and Brayton cycle? Anyone? I hope everybody was able to understand. That particular part is a bit kind of confusing. So that is the reason even I also dealt it very slowly. So if you have any questions to ask so far related to Rankine cycle and Brayton cycle, you may, or otherwise we can move forward to seeing some of the what do you say, some of the losses in the energy that happens during the steam generation process. So as such, when you basically generate steam, or when the energy is basically generated through steam, you typically have some sort of a losses in them. So we can look at those parameters before we move forward for energy production through plastics and gas cleanup. Anyone with any questions? Okay. So, as I said, the energy that you can actually generate or obtain through the steam oh yeah, 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 yeah. Hello. Actually speaking, the few oxygen to the fuel ratio, we typically keep it less than 0.68. So it actually people use it in a very like what do you say, kind of both the ways are equally acceptable. In some places you actually read it in absence of oxygen, and in some places you actually see it in a limited supply of oxygen. So both of them are equally fine. Yeah, yeah, exactly, exactly. Okay. So, yeah, as I was saying, in case of the steam generation process, what we usually do is we basically send. So, in a steam generator, we usually send both water as well as the fuel or the air, and that fuel as well as that of the air burns, and then that basically raises the temperature of the water, converting the liquid water to water vapor, or you can also call as the steam. But in this process of generating steam from water vapor, some amount of the energy is usually lost. So there are multiple factors on why this energy is basically getting lost. So whatever the amount of energy that you get from the steam generation process in the form of the steam is usually less. So there are losses of energy that is happening through this steam generation process. So now let's just look at each of these factors which are basically contributing to the loss in energy during the steam generation process. So the first process or the first reason for the energy loss is nothing but it is due to the moisture present in the feedstock. As you know, if you have moisture, some amount of the energy will be used up in order to you can say in order to remove the moisture from the system. So that energy is also typically going to be lost in that part in the steam generation process. The second loss is lost due to the unburnt carbon. So if you have any kind of unburnt carbon that is going to be present in the system, that will again lead to loss in energy. And then loss due to dry exhaust gas, and the fourth one is loss due to incomplete combustion. Fifth one is loss due to convection and radiation, that process that typically happens in case of the steam generation. So there will be losses due to convection and the radiation of the heat energy from the steam generation unit itself. Then you have energy loss due to slag or ash that gets generated as residues in the particular process. So all these factors typically affect the energy steam generation efficiency of the system. So each of these parameters, if you see in the course, you have a mathematical expression for them. So for better understanding of I mean for these mathematical expression, I would suggest to all of you to look at the uh, slides in the course. So I think all of these the losses due to various process and their mathematical expressions, you can you can go through that those in the first lecture of week 5. So energy efficiency improvement in thermal power plants 2 basically covers all the mathematical equations that are contributing to the loss of energy in the steam generation process. Now we move on towards energy production through plastic waste. So as you know, plastic um, is ubiquitous. So in everyday use, plastic is almost has become very common. For human life, plastic has become inevitable, to be specific. So so we have come so far that imagining a life without plastic is kind of very difficult. It may not be impossible, but it is very difficult. So we use plastic from the very starting in the morning to till the end of the day. We live with plastics. We use plastics in almost all the daily activities that we do. But one of the main concerns about this plastic is what happens to this plastics after its use is over. What is the fate of the waste plastic that are thrown after their lifetime is over? So this becomes a very important concern. Specifically, what usually happens is this waste plastic that are thrown sometimes majority of the times usually enters inside the ocean. So due to the ocean waves as well as the ocean currents, this plastic waste tends to undergo, or you can say it starts breaking down. So the waste plastic that ends up in the land remains there as non-biodegradable waste. So plastics are non-biodegradable in nature. So they tend to remain in the soil or in the land for thousands of years. Whereas the plastic that ends up in ocean, due to the ocean current and the ocean waves, actually break down, and then that basically results in the contamination of the ocean in the form of and contamination of the ocean in the form of microplastic and nanoplastics. So these micro and nanoplastic typically enters, so once it enters inside the ocean, it's there in the water bodies. This water mixes with the sea, river, everywhere, and then that water is something basically comes out as a drinking water which we drink. So it has become a process wherein the plastic waste that we throw in the land or in the ocean basically comes back to us in the form of drinking water. So if you happen to see the news in the last 1 or 2 years, you can see there are multiple incidents of microplastic contamination in food, in water, and also there are so many evidences where they have found microplastic even in the human body, in different organs, where they find where they found the microplastics to be present. So all these are basically, so this entire microplastic nanoplastic problem actually happened because of human beings. So one of the ways to basically um, kind of make sustainable use of this plastic is to basically extract energy from this waste plastic. So for that, for that, the process that we do is nothing but it is the thermal conversion process. So where the plastic materials are burnt and then their energy is extracted for the daily life applications, and then their residues are discarded away. So when you burn the waste plastic using the thermal conversion routes, you basically generate or produce oil. The oil that is produced from this waste plastic are typically of the higher quality compared to the oil that is produced from the biomass waste. So if you compare the quality of the oil from the biomass waste as well as that of the plastic waste, the plastic waste tend to produce oil which are of higher quality compared to the oil that gets generated from the biomass waste. Any idea on why this kind of difference usually happens, or difference usually arises? Anyone, any idea on that? Just a second. Yes. Any reason on why that the waste that gets the oil that is produced from the biomass waste are of high quality compared to the oil that is produced from the biomass? Sorry. Why is that the oil that is produced from the plastic waste is of higher quality compared to the oil that is produced from the biomass waste? Typically, the main reason is that the biomass waste are not going to be impurities free. The amount of impurities that are going to be present in the biomass will be high. They will be more contaminated in nature compared to the plastic waste that you can obtain. So the biomass waste, whatever you are going to be get in the as a sample, will not be 100% impurities free. There will be a lot of impurities that is actually going to be present in them. So due to which the quality of the oil that you get from the biomass waste will be inferior compared to the oil that is produced from the plastic waste. And again, it's not like that. So the if you see the mm, not all plastic waste are suitable for the energy generation process. So usually polyethylene and polypropylene have a good characteristics of fuel which can be uh, which can be used for these waste to energy generation process or for the production of the oil. So usually pyrolysis process is used for the conversion of the plastic waste to oil, or for you can say the waste to energy generation process. So typically two different types of pyrolysis processes used for producing energy from the waste plastic. So the first one is the thermal pyrolysis and second one is the catalytic pyrolysis. So one of the major advantage with respect to the catalytic pyrolysis compared to the thermal pyrolysis is that the use of catalyst actually tends to reduce the temperature of the process that is involved in this pyrolysis. So so if you so in case of thermal pyrolysis a much higher temperature is used, whereas in case of a catalysis process, catalytic pyrolysis, the energy generation is far lesser because of the use of the catalyst in them. So the catalyst drives the reaction much faster, so that basically reduces the amount of temperature that is required in the process. So the energy that we need to give into the process is reduced. So that becomes one of the main advantage of catalytic pyrolysis process. And then the second advantage is basically on the fuel quality. The fuel quality in case of the pyrolysis process for the production of oil from the plastic waste is better in the catalytic process. And in case of this catalytic pyrolysis process, different types of homogeneous and heterogeneous catalysts are typically used. Anyone with any examples for homogeneous and heterogeneous catalyst that is used in this oil production process from waste plastic? So the first one is the thermal pyrolysis. Thermal pyrolysis, and second one is the catalytic pyrolysis. So the major advantage, so in case of thermal pyrolysis, you basically employ heat in order to break down the plastic, or you can say in the engineering term polymers, into smaller components, or you can say in form of the oligomers, and then the liquid is basically produced from them, and usually they will have the liquid that is usually produced from this plastic waste will have a mixture of alkenes and alkynes. In case of catalytic pyrolysis process also we use temperature, but the temperature that we use in case of catalytic pyrolysis process will be much lesser compared to thermal pyrolysis, because of the use of catalyst, which reduces the amount of energy that is required for the burning process, and then the fuel quality in case of catalytic pyrolysis process is reduced. So the catalyst that is used in this catalytic pyrolysis process is of two categories. One is the homogeneous catalyst and another one is your heterogeneous catalyst. So my question is, any examples for these two homogeneous and heterogeneous catalysts? So in case of homogeneous catalyst, you can say compounds like FeCl3, AlCl3 can be used. And in case of heterogeneous catalyst, you can take examples like zeolites. They are a very good example for heterogeneous catalysts. FeCl3, that is ferric chloride, and aluminium chloride, AlCl3. And in case of heterogeneous catalysts, you have zeolites. They are an excellent example. So here ends the concept of energy production from plastic waste. So after this we have the gas cleanup. So that is nothing but whatever the amount of, or whatever the gas that gets generated from this process has to be cleaned up, because they are basically going to contain much amount of dust particles, soot particles and impurities that is present in them. So those needs to be cleaned up before the gas is actually released into the atmosphere. So if you see, there are certain standards that are set by CPCB, Central Pollution Control Board, for making sure that the gas that gets into the atmosphere is clean, so that it does not pollute the atmosphere. So one of the main concerns is this: even though we basically we produce waste energy from waste, and that is profitable in nature, but that does not mean whatever the waste gas that gets generated out of the system, we let them in the atmosphere as such. They need to be processed before they can enter inside the atmosphere. So for that particular process, we for that processing we use multiple techniques for cleaning up the gas. So you can say multiple techniques, in the sense multiple different types of equipments are used in order for cleaning up of the gas before it is actually let into the atmosphere. So first one is the gravity settler, so where gravity is used for settling of these particles, the soot particles, and then the clean air is basically let into the atmosphere. The second process is nothing but it's a gas scrubber, and then the third one and the most important one is the electrostatic precipitator. So electrostatic precipitator is basically uh, in this process what happens is you have electrodes, and then the flue gas is you have electrodes, and then they are basically connected to a high DC voltage supply. Now through this electric field that gets generated, the flue gas is sent in between the electrode plates. So because of the very high DC voltage, a very high electric field is maintained between these electrode plates, and when the flue gas enters in between these electrode plates, what happens is they actually gets ionized, and then the particulate matter that is present in this flue gas actually acquire negative charge. So now you have flue gas with a negatively charged particulate matter, or you can say the soot particles. Now these negatively charged particles get attracted to the positive plate, which are called as the collection plate. So if you see, this is the collector plate. So you have two collector plate, and then the negatively charged particulate matter gets attracted to this positively charged collector plate, and gets stuck to them. So they basically get stuck to these collector plates. Then the particulate matter from these collector plates are usually scrapped off. They usually form a layer as the process continue. Once after a certain period of time, these plates are disconnected, and then the particulate matter is removed. So in this process, the flue gas that gets through this electrostatic precipitator gets purified. So process as such is very simple. So you send the flue gas between the collector plates, and a very high DC voltage is applied in between these two plates, which basically results in a high electric field. Now when the flue gas actually enters inside these collector plates and experiences the high electric field, they tend to get ionized. So when they get ionized, the particulate matter that is present in them, which we want to remove, gets negatively charged. These negatively charged particles are attracted to the positively charged collection plate. So negative and positive charge attract each other. Opposite charges attracts each other. So the negatively charged particulate matter are attracted to the positively charged collection plate on either sides. Now once they are attracted, as the process keeps on continuing and more amount of the gas keeps flowing in between these two plates, a layer of the particulate matter is formed in both of these collection plate. Once after a particular time is reached where no more particulate matter can be absorbed on can be, or you can say, absorbed or stuck onto that collector plate, this entire arrangement is disconnected, and then the layer of particulate matter is scraped off before it can be used for the next cycle of purification. So in this process, as the particulate matter gets what do you say gets attracted to the collection plate, the flue gas becomes free of the particulate matter and is then, so thus it gets cleaned up and is now basically discharged into the atmosphere. So this electrostatic precipitator only works on the principle of electrostatics. So that's why it is called electrostatic precipitator. So the particles are precipitated um, using electrostatic or is the precipitation process is driven by electrostatic mechanism. And this process and this type of ESP or electrostatic precipitator is called parallel plate type ESPs. So here you use parallel collection plates for collecting the particulate matter from the flue gas. So any questions so far related to this energy production from plastic waste and gas cleanup? Because gas cleanup ends here. This is something that I wanted to discuss, electrostatic precipitator. Anyone with any questions? So the electric field, since we apply a high DC voltage, which is going to be very strong. So that's how the flue gas, whatever is entering between these collection plates, are ionized. This electrostatic precipitator concept is something that will be more commonly available in industrial plants. So they tend to use electrostatic precipitators for cleaning up of the gas that gets generated in their system before it is let out to the atmosphere. Anyone with any questions on electrostatic precipitator or energy production from plastic waste? Plastic waste energy production is simple, it's just a thermal pyrolysis process. Over here, by burning plastic waste, you are going to get oil, and that oil is basically of very good quality compared to that of the biomass waste. In order to generate oil from this plastic waste, you use two process, thermal and catalytic pyrolysis. So if you have no questions, then let's move on towards some multiple choice questions and then numerical problems. So the first question is, any doubts before that? Again, let me just ask once again, any doubts so far? Okay. So the first question, disposable coffee cup, plastic food boxes, plastic cutlery and packing foam are mostly produced from polystyrene, polypropylene, low density polyethylene and high density polyethylene. Disposable coffee cups, plastic food boxes, plastic cutleries and packing foam. Yes, anyone? This is a direct question. You can actually, if you see the slides, um, you will have polymers and then their typical examples. So, any answers or shall I show the answers? Okay, so no one. So, let me show the table for you guys. So, oh, so this is a polymer and this is typical examples of where this polymer is used. So this particular table is adapted from your course slides. So if you see, even in the course slides you will have the same table available. So this list typically contains what polymer and where they are used. So if you see PET, they are used in the form of bottles, medicine jars, ropes, clothing and carpet fiber. Like that you have for HDPE, LDPE, PVC, PP, PS and others. So if you see for polystyrene, you have disposable coffee cups, plastic box, plus plastic cutleries and packing foams. All of these items are usually made up of PS, that is your polystyrene. So here the answer is polystyrene. You need to remember this because this is a direct question. So you need to either guess which polymer. So you can actually make a, what do you say, educated guess here. So if you see LDP and HDP, they are typically used in case of polythene bags and squeezable bottles, mainly in the form of like containers for milk or soap bottles, so which do not require much rigidity, whereas in case of disposable coffee cup and plastic food boxes they require certain level of you can say rigidity in them, so there polystyrene is used and not polypropylene or what do you say, HDPE or LDPE. So please have a kind of a, please make yourself familiar with a few examples for each type of polymers because these questions are something which you can actually expect during your final exams as well. So, which of the following is not the advantage of screw reactor? It's a continuous process, better mixing properties, easy of scale up and none of the above. So screw reactors are the type of reactors that is usually used for energy production from plastic waste. So there you will typically discuss about four different types of reactors. One is a fixed bed, fluidized bed, screw reactor and a conical spouted bed reactor. So now we need to know which of the following is not the advantage of a screw reactor. The question says which of the following is not an advantage. Continuous process is an advantage for screw reactors. Screw reactor does operate under continuous process conditions. So as I said the answer, so this is not the correct answer for this question. Easy of scale up, yes. So screw reactors has two type of advantage. One is it's a continuous process and another one is a better mixing properties. However, the easy of scale up is not the advantage of a screw reactor. Now let's leave question 3 because we didn't deal about scrubbers, which we will do it in the next live interaction session. Before that, let's move on towards other question. Fill in the table and comment about their usability for liquid fuel production. So you have column A where in some you have the polymer name, and so column A is for polymer name and column B is for their structure. So in few of the rows, if you see, you have the polymer name but not their structures. So you need to tell me what will be their monomers, and in few of them you have the monomers but not the polymers, so you need to tell me the polymer name. So column A is for polymer and column B is for their respective monomers. And after filling in the table, you need to comment about their usability for the liquid fuel production. So HDPE, high density polyethylene, what will be the monomer? Just a second. High density polyethylene, what is a monomer? Oh, let me just write this in case. Column A is polymer name, or you can say simply polymer, and B is for their respective monomer. So in column A you have HDPE, that is high density polyethylene. What will be the corresponding monomer, or what will be their corresponding monomer? Oh, sorry, there was a network issue, so I hope the disruption did not happen long before. uh, yeah. Screen is visible, I believe. So column A is for the polymer name and column B is for the monomer. So for HDPE, what will be its respective monomer? HDPE is high density polyethylene. High density polyethylene. Polyethylene. So their respective monomers is ethene. So CH2 double bond CH2. Now for the next one, the monomer is CH2 double bond CHCl. So what will be their polymer, or what polymer can be made from this monomer? Vinyl chloride. Okay, that is the monomer name. That's correct. The monomer name is vinyl chloride. So what will be the polymer that we can form using vinyl chloride? Polyvinyl chloride. Polyvinyl chloride. Is it right? PVC. PVC is something that you use in your homes as well. The pipes, the plastic pipes are made up of PVC. And many of you may have actually heard PVC name before also, but may not be sure of their respective monomer. So next question is, so next one, you have the monomer, you have two monomers. So here they will not undergo addition polymerization unlike in the other two. This will be an example of condensation polymerization. So the first one is CH2 NH, the first monomer is NH2 CH2 6 times NH2, and second one is COOH CH2 6 times COOH. That is, the first one is hexamethylene diamine and second one is adipic acid. So if these two monomers undergo condensation polymerization, what will be the polymer name? Typically what happens in condensation polymerization is water molecules, when these two monomers combine, water molecules get eliminated. And then they form a polymer. So which polymer usually use hexamethylene diamine and adipic acid as their monomer? Yes, anyone? These no monomer, these names we will, most of us will be familiar with. All of these, what do you say, examples that I have given here, that is given in the question, are something that we are familiar with before itself. Most of us would have learnt these polymers and then their monomers back in their school days. So the polymer name is nylon 6, 6. Okay, can anyone tell me why do we write nylon 6 comma 6? Why is that 6 comma 6 here? It can be just nylon. Why this 6 comma 6? Nylon 6 comma 6. Because we have 6 CH2 groups in both hexamethylene diamine monomer and adipic acid monomer. If you see here CH26 and here also CH26. That is the reason we call this particular polymer as nylon 6 comma 6. Let's come to the next polymer. Here we are given the name of the polymer and we are asked what will be its monomer. PS, that is polystyrene. So what will be its respective monomer? Anyone? Oh, it somebody has given styrene. Yes. So for PS it will be styrene, and there was another one. No, all the answers were given here or what? Okay. Then next one. Okay, styrene. But what will be the formula for styrene molecule? So it is C6H5 CH double bond CH2. Next we have PP, which is polypropylene. So what will be their respective monomer for polypropylene? So for polystyrene, monomer is styrene. For polypropylene, monomer will be propene. Yes. So it will be like CH3 CH double bond. Oh, sorry, double bond CH2 propene. After that, we have three monomers: acrylonitrile butadiene styrene. What will be the polymer? ABS, acrylobutadiene styrene. So this will be the polymer name for, for this will be the name of the polymer which is synthesized through acrylonitrile butadiene styrene. It's actually a form of rubber, ABS rubber. So kindly have a look add the polymer names along with their monomers, because these kind of questions may also be, you can actually see these kind of questions in your exams as well as in your assignments also, hopefully. So now let's move on to question 5. Identify the type of reactor used in this pyrolysis process of plastic waste, of our plastic waste. Is it a conical spouted bed reactor, fixed bed reactor, or fluidized bed reactor, or a screw reactor? Option A. Yes, it's a conical spouted bed reactor. So this ends with the MCQs here. Any questions so far for in all the four questions that we discussed? Now I have one question in question 4. So HDP is high density polythene, and for that the monomer is ethene, CH2 double bond CH2. What will be the monomer for LDP, low density polyethylene? Monomer for LDP. What about for LDPE? Let me will I be able to insert a column? Okay. Mm. LDPE, low density polythene. It will be same ethene monomer, but then there is a difference between both of them. It will be same. The monomer is going to be same in both case of LDPE and HDPE. But HDPE is different compared to that of the LDPE, and then the applications where HDPE and LDPE is used is also going to be different. Now, what are the differences, if anyone knows? Does anyone know what is the difference between HDPE or LDPE? How they both are typically different, even though they are basically synthesized from ethene monomer, but HDPE and LDPE are different from one another, and then their targeted applications or use is also different. So have a look at it of what is actually the difference between HDPE and LDPE, and how they are different from one another, and why. I mean, like why. what is their targeted use, and why is it so. So that will be, I mean, that will be useful for you to know what is the difference between them. So have a look at that in your free time. So next, let's move on towards questions. So let me just give um, mm. So this is the question for today. So let's start here, because those two questions were for previous, from previous live interaction session which we didn't complete. So let's first finish question 8, then we'll move to question 7. Calculate the thermal efficiency of the power plant if the heat rate generated is 3233 kcal per kilowatt hour. If the heat rate is 3233 kcal per kilowatt hour, what will be the thermal efficiency of the power plant? How to calculate this question, for this question? What's the formula for calculating the thermal efficiency of the power plant if the heat rate generated is given to us? Yes. So let me give the formula. So then I think I'll be able to. Some of you may be finding, may not be knowing the formula. So thermal efficiency percentage is nothing but it is 100 by HR. As I said, heat rate is nothing but it is 1 by thermal efficiency. So since we are basically we need to express the efficiency in terms of percentage, so it is 100 by heat rate. So based on this, what will be the answer? Yes, anyone with answer? No. Okay. So let me start solving it. So thermal efficiency in terms of percentage is 3233. So if I use, let me just use. So it's going to be 0.0309 percentage. Is this correct? Thermal efficiency is 0.0309 percentage. That's very small. Am I making some mistake somewhere? Or am I missing am I missing something here? So here we one thing that we missed out is the units. If you see the heat rate that is generated, it is in kilocal per kilowatt hour. However, the thermal efficiency what we actually want is in terms of percentage. So now we need to take the factor of how if of we need to convert this kilowatt hour into kilocalories. So now we need to basically introduce a conversion factor. So 1 kilowatt hour equals 859.845 kilocal. Now based on this, if you do the calculation, then thermal efficiency is, if you introduce this conversion factor, then it would be 100 times 859.845, the whole divided by 3233. That would be 26.595%. So the thermal efficiency of the power plant, which basically generates heat, or the heat rate that is generated, is 3233 kilowatt per kilocal per kilowatt hour, is 26.595 percentage. Any questions in this? Because this is a simple calculations, but if you have any doubts, please let me know. We can solve one or two more problems before today's session ends. Anyone? If I don't ask in terms of, or if probably the options are not given in terms of percentage, if it is just on the part of thermal efficiency, then you don't need to have that 100 in the numerator. So you don't need to multiply with 100 in the numerator. Then it would be 0.26 would be the thermal efficiency, but not in terms of percentage. So let's just a second. Mm, okay, let's move on to question 10. Because I first want to finish questions that will take much longer time. Then we have two more which will not take much time. So let's first see question 10. A MSW municipal solid waste based power plant is emitting 33,000 meter cube per hour of flue gas. It is proposed to install an ESP for the gas cleanup before releasing it out in the atmosphere. Total area available for the collection electrode is 300 meter square. Drift velocity of the particle is 0.2 meter per second. Calculate the efficiency of the ESP that can be installed within this area. Next, considering the fact that we require an ESP will have a collection efficiency greater than 97%, calculate for the additional area that will be required to accommodate the space for the collection electrodes. So first question is, based on the given data, we need to calculate the efficiency. Now, in the second question, we are given with a particular efficiency for a process, and we have certain area that is available for the correction electrode. Now, we need to see how much more additional area will be required by these collector electrodes. How to calculate the efficiency of the electrostatic precipitator? Anyone? How to calculate the efficiency of the ESP? So let me give the formula. E equals to 1 minus exponential of minus Vm times A by Q, where Vm is the drift velocity. Let me just a second. Where Vm is nothing but it's the drift velocity. A is the total area available for the collector electrodes, and Q is the rate of flue gas that is entering inside the ESP. Now based on this, calculate the efficiency of the ESP that can be installed in the given area. So it's just about substitution from here. So Vm is nothing but it is the drift velocity of the particle, which its value is zero point 0.2 meter per second, and your area, that is the area of the collector electrodes, is 300 meters square, and your Q is 33,000 meter cube per hour. Now since everything is in its SI unit, we need to convert hour to seconds. So Q is nothing but 33,000 divided by 3,600. 1 hour has 3,600 seconds. So if we do that, then divided by 3,600, so it will be 9.16 meter per meter cube per second. So if we substitute this in this expression, then it will be 1 minus exponential of minus 300 times zero point 0.2 divided by 9.16. So 300 times zero point 0.2 is minus 60 by 9.16. 60 by 9.16 is 6.55. So Just a second. The value is 1 minus 0.014. I'm not wrong. 0.0014. Okay. So that would be 0.9986. If you express this in the form of percentage, it is 99.86%. So the efficiency of the ESP that can be installed within this area is 99.86 percentage. Any questions? So this is simple. If you know the formula, it's about substitution. So we are given with the drift velocity, area and the flow rate or the flue gas flow rate. You just need to convert the flue gas flow rate from meter cube per hour to meter cube per second, and then if you substitute in the formula, you will be able to calculate the efficiency of the process, which here turns out to be 99.86. Now based on this, let's look at the option B, question B. Considering the fact that we require an ESP with a collection efficiency greater than 97%, calculate the additional area required to accommodate the space for the collection electrode. Well, how to answer this, or what will be the answer? Any guesses? So the question says that we require an ESP that is greater than 97%. But the efficiency of the collector that we have got is 99.86%. So it's already 2.86% greater than what we actually require. So 300 meter square area for the collector electrodes is far more sufficient to obtain the required efficiency percentage. So no additional area will be required to accommodate the space for the collector electrodes. So option B, the answer, numerical answer is 0. So since ESP efficiency is greater than 97 percentage with the available connection electrode, no additional space is required. Sorry, 1 minute. Is required. So this is the answer for question 10B. Any doubts with question 10 so far? We will stop our session here. So if you have any doubt, let me know, because it's already, I guess, 7:23. So yeah. Anyone, any questions? Let me just stop sharing. Any questions, anyone? Okay, so if you have no questions, then shall we conclude the session? Okay, so thank you all for joining today's live interaction session. The the recording as well as the presentation will be uploaded by next week. You will be able to access it from the Excel sheet that is available in the course page. So I take this as an opportunity to thank Professor Prasenjit Mondal sir as well as the NPTEL team for providing me the opportunity to interact with you all on this Sunday afternoon. Our next live interaction session will be on 1st March from 5 p.m. to 7 p.m. I hope to meet you all there. Till then, keep solving on your assignment problems as well as on the problems that we are discussing in the live interaction session. And in case if you have any doubts, you are welcome to email me. So thank you and have a great weekend ahead as well as a great week. Bye.